form of stereoisomerism we're going to be discussing is optical isomerism. And what do we mean by that? Optical isomerism is a form of stereoisomerism in which there is a difference in a spatial arrangement of atoms to give non-superimposable mirror images of the compound. So when we refer to non-superimposable images, we are looking at images that are not identical to the object. Images that are not identical to the object. When you have an image and an object and they are not identical, what you refer to them as are non-superimposable images. But let's not concentrate on that. Let's look at the organic chemistry relation to this. Now, for a compound to exhibit optical isomerism, it simply means that the compound has the ability to turn the plane of a polarized light towards the left or towards the right. That is what optical activity simply means. When you say optical activity is the ability of a compound to turn the plane of a polarized light. So when it changes the direction towards the left or turns the plane towards the right, what simply happens is optical isomerism. Now, for any compound to exhibit optical activity or optical isomerism, it must possess what we refer to as a chiral carbon atom. A chiral carbon atom is a carbon atom that is directly attached to 4 different things. Once an organic compound has a carbon atom which is directly attached to 4 different species, automatically it is referred to as a chiral carbon. Hence, it becomes optically active. Okay, so let's look at an example to help us understand this. Imagine, for instance, I have this compound. Let's say, 3-methyl hexane. So let's fill the hydrogens. 3, this is going to be 2, and this is going to be hydrogen here. This is 2, this is 2, this is 3. Okay, so if you consider this particular compound, this is actually the least alkane which is optically active. The least alkane that has or exhibits optical activity is your 3-methyl hexane. So you will notice that on this side, you have an ethyl group. Here, you have hydrogen. Here, you have 3 carbon atoms, which is propyl group, and here, you have just 1 carbon atom, which is methyl group. So you notice that this particular carbon atom is what we refer to as a chiral carbon. Why? It is directly attached to 4 different species. Hence, it is optically active. What does it mean? It means that this particular compound can exhibit optical isomerism. That is, it either turns the plane towards the right or turns the plane towards the left. Let's consider another compound that can exhibit optical isomerism or is optically active. Remember, I told you, for a compound to exhibit optical isomerism, it must possess a chiral carbon. The second compound is alanine, whose IUPAC name is 2-amine propanoic acid. So let's look at that. What is 2-amine propanoic acid? You have C. Let me use a different color to make it clearer. So you have C, and then you have the amine, 2-amine. The oic acid is COOH. Then you have hydrogen here. You fill the hydrogen, 3. Okay, so we have this. Now, with this said, you will notice that we have a chiral carbon here. How do I know? This particular carbon atom is attached to 4 different species. Let's confirm that. So you have here, it is attached to a methyl group on this side. On this other side, it is attached to hydrogen. On the other side, it is attached to a carboxylic group. And then finally, you have an amine group here. So what does this indicate? It simply implies that you have 4 different species around it, hence making this carbon atom a chiral carbon atom or a chiral center. You either call it a chiral carbon or a chiral center. Same here, you have that this carbon atom is a chiral center. And any compound, organic compound that possesses a chiral center becomes optically active. Let's consider the compounds on the screen and see if they actually exhibit optical isomerism. On the screen, you have glucose and fructose. First of all, I would like you to understand that glucose is an alkyl. Yes, an aldehyde. Yes. Why is it an aldehyde? It possesses a terminal carbonyl group. So if you notice, the carbonyl group of glucose is terminal at the last carbon atom. And fructose is an alkanone because the carbonyl group is non-terminal. So if we are to name or give the IUPAC nomenclature of glucose, it is going to be, let's number it. So you have 1, 2, 3, 4, 5, 6. So this is going to be 2, 3, 4, 5, 6 pentahydroxyhexanal. Yes, 2, 3, 4, 5, 6 pentahydroxyhexanal. Let me see if I can get that into this. Pentahydroxyhexanal. Yes, and then here you have 1, 3, 4, 5, 6. 1, 3, 4, 5, 6 pentahydroxyhexanol, because it possesses a non-terminal carbon atom. So let's come back to the optical activity of glucose. Now, if you look at this, you will notice that carbon atoms number 2, 3, 4, and 5 are actually chiral carbon atoms. Why? They are attached to 4 different species. You have, for instance, in this guy, you have hydrogen attached here, you have hydroxyl attached here, you have this particular group which has 4 carbon atoms and hydroxyl group down, and then you have your carbonyl group attached here, which is 4 different species, which means that this is a chiral carbon. If you look at it again, you also notice that 3 is also a chiral carbon, 4 chiral carbon, and 5 chiral carbon. So chiral carbons existing in glucose include 2, 3, 4, and 5. In fructose, you have the chiral carbons existing also include number here you have 3, 4, and number 5. These particular 3 exhibit optical isomerism. 3, 4, 5 exhibits optical isomerism, or are chiral carbons of fructose, while 2, 3, 4, and 5 are chiral carbons of glucose. With that said, I hope this has been helpful, which means that glucose and fructose both exhibit optical isomerism. Having understood optical activity and its relation to chiral carbon, it is also important to note that compounds that exhibit optical isomerism or are optically active are referred to as enantiomers. Enantiomers. And there are 2 major types of enantiomers, which are levoenantiomers and dextroenantiomers. So the levoenantiomers turn the polarized light towards the left. I actually use this to remember LL, so levo left. Dextro would have to be the other one, which is right. So you have that the levoenantiomers will turn the plane of the polarized light towards the left, while the dextroenantiomers will turn the plane of the polarized light towards the right. So when we say that a compound is a levoenantiomer, what do we simply mean? As I said, it simply turns the plane of the polarized light towards the left. So let's consider a compound. For instance, fructose. Fructose solutions are majorly levoenantiomers. Yes, they turn the plane of polarized light towards the left. If you have, for instance, a particular solution of fructose, let's call this, this is our left side and this is our right side. If the plane of the polarized light is traveling through a fructose solution, automatically it begins to turn it towards the left. Hence, what is exhibited here is levoenantiomerism, which means that this, for instance, is a levoenantiomer. And I told you a very good example of your levoenantiomers is your L-fructose. Now, the major fructose that exists is the L-fructose, which is the levoenantiomer fructose. When you see L-fructose, it means the levoenantiomer fructose. Now, when you consider glucose, for instance, glucose majorly exists as dextroenantiomers. That's why we refer to them as D-glucose. D-glucose or dextrose. When you say dextrose, you mean the D-glucose. And the D-glucose is a dextroenantiomer which will turn the plane of a polarized light towards the right. It will turn the plane of a polarized light towards the right. So you have that. And that is what we refer to as optical isomerism. A scenario where the plane of a polarized light is turned either towards the left or towards the right. With this said, I hope you've learned a lot in this video. Remember, this is Weight Stout.